So I'll begin with this talking about the signal recycling interferometer, which was first, the initial motivation of the signal recycling interferometer was actually not to change the dynamics. Instead, it's motivated from the optics, because people start thinking that adding more mirrors into the interferometer design will add more optical resonances into the system and thereby give more richness to the noise curve. For example, this was first investigated by Driver in '82 and Mears in '88. And this particular design of adding one mirror into the dark port of the interferometer was designed by Mears. And it's called a signal recycling interferometer. So in order to understand the interferometer, we first have to recall the fact that this is a Michelson configuration where the carrier light laser enters here and build up a symmetric excitation in the two cavities, and the light will come into the arm cavities and come back directly to the laser without being affected by whatever you put into the dark port. So by adding this mirror here, we won't affect the carrier light. And however, the gravitational wave sideband that we're interested in is the anti-symmetric mode. And those lights will go out from this dark port and come back. So it is directly interacting with this signal recycling mirror, and it will behave quite differently from the carrier. And there is possible resonances, optical resonances of the new system. And another thing I want to say is that in the particular design of LIGO 2, for example, or GEO, the distance between this arm cavity internal mirror and the signal recycling mirror is quite small. So the phase shift gained by all the relevant lights, for example, the carrier light and all the gravitational wave sidebands, the phase gain will be the same. So we can effectively put another single mirror here to incorporate these signal recycling effects to the gravitational wave sidebands. So here in this transparency, I'll just first talk about the optical resonance of a signal recycling interferometer at low powers, where this is the original idea of the signal recycling interferometer. So as I have said, it's possible to look at the signal recycling interferometer schematically in this simplified scheme, where we have two reference planes here representing the arm, and the carrier is built up here statically in a very large amplitude. And we have an effective signal recycling cavity with transmissivity T, and there is an effective round-trip phase inside this small portion of length, with the same phase gain for both the carrier and the gravitational wave sideband.
So we're to imagine there is a mirror at the left edge of where the dark red is?
Yeah. So it's this effective mirror incorporates both mirrors, the signal recycling cavity. And when the test mass moves at the frequency omega, it will phase modulate, as Alessandra has said. Phase modulate the carrier and generate this green modulation gravitational wave sideband. It consists of frequency components different from the carrier, omega by plus or minus omega, which omega is the motion frequency. So it is possible that when this condition of 2 omega L over C plus the round-trip phase phi when this is equal to 2m pi, there could be a resonance of this gravitational wave sideband. And the width of the resonance will be determined by the half bandwidth of the resonance, which is Tc over 4L, and T is the transmissivity of this effective signal recycling cavity. And if the gravitational wave is at that frequency or nearby, then there will be it will bounce back and forth for a lot of times inside the cavity and gain a lot of amplifications. While if the gravitational wave is away from that, it doesn't gain a lot. So there is effectively a resonance. So if this phi, so it depends also on the phase shift of this phi. If this phi is 0 or pi for the carrier frequency, then the resonance is on the carrier frequency. It's for omega equal to 0, so it's not quite interesting. But if this phi is quite generic, or what we call the detuned case, where it is not equal to 0 or pi, then there will be effectively a valley in the noise curve at the resonant position. And this will allow people to do narrowbanding or move the frequency to relevant astrophysical sources to gain specific sensitivity at interested sources. But when the laser power is quite strong, we also have to worry about radiation pressure. And here we have a similar diagram that Alessandra has drawn for the conventional interferometer, but much more, a little bit more complicated. So let's put another, so since we are going to consider the radiation pressure noise, it's better to decompose the fields into the amplitude and phase modulations. So in whatever symbol I have here, I have the carrier component in the first entry and the amplitude modulation in the second and phase modulation in the end. Suppose we have a reference plane here for our input vacuum field, and the distance from this plane to that plane is 2 pi, for example. And so here is on resonance with the carrier, but here we have a phase, round-trip phase. So let's consider this system recursively. So let's suppose we have a little bit of photon which consists of some amplitude and phase modulations here and enters in the first time into this arm. Initially, it'll gain the carrier. The carrier is always there, and there is amplitude modulation and the phase modulation. It'll bounce back from the mirror so that it'll be phase modulated. So I show here the phase modulation now contains the motion information of the mirror. However, when you see that this guy will now come here and go back, bounced by this mirror. So since usually if you have a round-trip phase of phi, it turns out if this is the amplitude and phase modulations of this light coming in this way, when it returns to here, the amplitude and phase quadratures will be rotated by this angle phi. Of course, only part of it comes back, while the other part is replaced by part of the vacuum fluctuations. So at this moment, the light that comes this way will contain, both the amplitude and phase modulations of this light will contain the displacement information, and the amplitude and phase quadratures are somewhat mixed. So in this case, and then this light will go on and get bounced back and forth and on and on. So for this system, you have displacement information both in the amplitude and phase quadratures. And amplitude and phase quadratures are mixed together. So we also remember from Alessandra's discussion that the phase quadrature contains the shot noise, while the amplitude quadrature is more the radiation pressure noise. So effectively, this thing will suggest that the phase and amplitude, the shot and radiation pressure noise are correlated. But this is not quite intuitive. The more interesting thing is that since we see from here that the amplitude modulations of the lights of the carrier here contains gravitational wave displacements. So this will mean that the radiation pressure noise will really depend on the motion of the mirror. And this is quite interesting. So here we schematically write that the force acting on the mirror will consist of the vacuum fluctuations that come in from the dark part, but it also contains a term that depends on the displacement with some response function we denoted by RFF of it's frequency dependent. This fact, so since the force is depending on the displacement of the mirror, let's write out the equation of motion of these, the displacement of the mirror. So if we write the Newton's equation, we have, this is basically mass times acceleration. It will be equal to the force due to the gravitational wave where we're in the proper reference frame. So the gravitational wave can be thought of as a force. So we also have the fluctuation, and we also have a part that depends on the displacement of the mirror. So this can also be thought of as you have an effective restoring force with a frequency-dependent spring constant. And as it turns out, this spring constant depends on the circulating power inside the arm cavity, which is quite natural. It also depends on reflectivity of the signal recycling mirror. It will also depend on the detuning of the signal recycling cavity. So if we move this term here, we will see that the equation of motion of the mirror will be of this form. And if at some frequency this becomes 0, then there will be a resonance of the system. So at this moment, we see that the signal recycling interferometer is not only a measurement device. It doesn't only samples the gravitational wave motion, but it also interacts non-trivially with this mirror test mass, so that the test mass are no longer free masses. And so naturally, people would think that the standard quantum limit might not be really, the free mass standard quantum limit might not be quite relevant. So let's look at a bit more at the detail of the dynamics. So here I'm plotting the response function of the force to the displacement, or effectively, another way of saying is that this is the frequency-dependent spring constant. And here, it is quite flat at low frequencies, while here it reaches a peak at the frequency where it is actually the optical resonance of the signal recycling interferometer, and it drops here. And so this kind of spring constant is quite analogous to the case where you have a massive spring with internal modes connected with the test mass. So when the test mass is moving quite slowly here, we're corresponding to this region, where the spring constant is really quite constant, and we're having a mechanical resonance. But if the mirror is moving quite high frequency near this range, then the internal mode of the spring, or in our case, is actually the optical mode of the interferometer is excited, so we have another resonance. So as it turns out, the interferometer gain sensitivity at these two resonances as shown by Alessandra in one of these previous noise curves. So for a typical configuration of this LIGO 2 signal recycling interferometer, we have two resonances here, and the noise curve really get two dips. And especially this one is beating the standard quantum limit by a factor of 2.
There are two noise curves shown there. Can you just explain?
These are detecting using different Homonide detection phases at the dartboard.
So you can make a choice.
Yeah, you have some flexibility of choosing that, but yeah. So this is a more, okay, let me come back to here. So here is the spring constant, and naturally, one natural thing is that to consider, because at low laser powers, actually, this spring constant is quite small. It's not quite interesting, but only when your laser power is high, this radiation pressure effect begins to take effect. So in this plot, I'm plotting the poles of the dynamical system in the complex frequency. This is the real part of the frequency, the imaginary part. I just plot their trajectories in this complex frequency plane as we increase the circulating power. So for this, these are the resonances of the system when when the laser power is very low. So this one is effectively free mass resonances, where you have a zero frequency resonance. And these two are the optical resonances. So as we can see that when you increase the laser power, especially this one, the real part of the mechanical resonance begins to be shifted. And this is the that I talked about, because you have a restoring force. So this is effectively an harmonic oscillator behavior. But the bad thing is that when you increase the laser power, these poles move into the positive imaginary, positive in the wrong plane, because it's above the real axis, and this means instabilities in the system. While this optical resonance still remain stable. So this is a big problem, because we cannot really do any measurement with an unstable system. So control systems has to be designed for this interferometer. So one example, Alessandra and I have thought about was that ideally, if you take some part of the dartboard output and apply a linear filter on it, and then feed it back as a force on test masses, you will be able actually to make the dynamical system stable again. And since we're taking the signal here and feeding back into the same degree of freedom as the gravitational wave force is acting on, it can be shown that the noise spectral density is not going to change. So the two noise curves I shown is still okay. But there might be some subtleties on the electronic systems that we have not worked out, and we're collaborating with Nergis in LIGO on that issue. Also, there's the issue of choice of readout scheme, which is technical, and I don't want to go into details, where you can choose between homodynamic detection and hemodynamic modulation techniques. So here I show the poles, the locus, pole locus of the system when you have the control system applied. So you can really see that this mechanical resonance is moved down and stabilized, while the optical resonance is still there, not changing. So there's, to be complete on this thing, we also have to consider the optical losses at different positions of the interferometers, where you have a loss in the arm cavities. We have assumed like 200 ppm loss per round trip, and there's also a portion of the photon loss bouncing off the secretly cycling interferometer, and there's also the photo detection efficiency. We'll be assuming numbers that are probably okay in the next 5 years, and so as a measure of the effect of the loss, we have calculated. So these two, we have calculated the noise spectral densities. Has calculated the signal to noise ratios for Newtonian chirps. So for a typical configuration, we can have a loss of the signal to noise of 8% or 21% of, well, these are just examples, determined by which quadrature you're looking at. For example, this 8% loss corresponds to the B1 quadrature, where it's shown in this green curve. And the dash curve is without loss, and the green curve is with loss. These are the spectral densities. So, and this B2 is this blue one, and it's quite. I think it's quite natural that because this guy has a more deep resonance, so the loss is more significant into this configuration. So we have a much stronger loss, signature loss. But overall, this is not a very significant effect, because still beats the standard continuity by a similar factor.
Still, and 20% loss of signal to noise.
It's 8%.
No, but the other one is 21%.
Yes, well, the one on the right is 21%, and that's going to extrapolate into about a 75.
Well, I guess
a rather significant loss of event rate.
Yes. Well, that is a practical issue where, in the optimization, we really have to choose which quadrature we're looking at, and because also taking into account other sources of noise, which I'm going to talk about later. But then you have to consider everything. Yeah, it could be so. Anyways, so there are also extensions of this design if you apply some techniques of squeeze light in the dartboard, or addition of this another mirror, for example. It's just examples where you can extend this thing we were thinking about. I'm not sure. Okay, so then after talking about the single second interferometer optical noise itself, we also have to consider other sources of noises, and then only after you take everything into account, then you can optimize the system. For example, just show examples of some current estimates of the thermal noises. With this is with silicon mirrors, where the internal thermal noise of this curve is quite important. It's quite large, and then it seems you have no hope of beating the standard quantum limit in this configuration. This is so, but with sapphire mirror, where people originally motivated using it by the fact that this internal thermal noise of sapphire is quite low. It's quite nice. But there is also the thermoelastic noise that we heard about a week ago. where as it is, it poses a big problem because this red curve shown here is the thermoelastic noise, while the black one is the standard quantum limit. And this guy is sitting above that. And then, in the end, as it is, using the current, the spherical mirrors and Gaussian modes, you're not able to beat the standard quantum limit, and it's that. And but however, as Kip talked about some time ago, and also in the homework, there is it's also possible. I forget this curve. Okay, it's also possible using flattened mirrors, which has like better, more flat optical modes, so that the thermoelastic noise can be lowered. And this is done by Kip and Erica D'Ambrosio, which are shown here, and also the group of Progusky in Moscow. So once you can lower the thermoelastic noise to 1/3 the standard quantum limit, as with respect to here, you see that this is like 1.5 the standard quantum limit. So once you have that done, you can really take advantage of that. So here I show two noise curves. Here is the previous curve, where you have the standard or the present thermoelastic noise estimate. Where here it is using the flattened optical mode. So you can really improve a lot. And in fact, if you calculate the numbers, it seems this guy is able to see neutron star mergers at 200 megaparsec.
That should be 300.
Yeah, well, it's old transparency. Yeah, right. I think yeah, you're right. So it is.
200 should be 300, and the 450.
It's 300 and 450. The 450 is right.
I see.
Yeah, I think it's a bit weird because it should be lower. Anyway, so it is a big improvement, and the important thing academically is that you can beat the standard quantum limit. So there are also some thoughts about not using other optical designs, but just playing with the figures with this design and see how you can push different regimes of the signal recycling interferometer. For example, one thing is that in a low frequency regime, where in order to take advantage of this optical noise, you first have to get rid of the thermal noise by using cryogenic probably techniques, which is investigated in Japan and Britain, Scotland, Glasgow. Anyway, and so apart from this, then the radiation pressure noise is more important because we're in a low frequency regime. And the two things you do is that you either get larger mass in the mirrors, or you use low laser powers. But as the curve shown here, it needs 100 or 200 kilograms, and but so you lower the. And there's also in this region important seismic noise and seismic gravity gradient noise. So in this curve, I'm showing this is the optical noise using this 200 kilograms and 200 kilowatt circuit. This is not high, but this is quite big. But David Shoemaker actually had this parameter, and he said it might be okay in a time frame of like several years, 5 years, 10 years. And this is the seismic noise, the gravity gradient. By the way, the gravity gradient noise is caused by motions of the Earth's ground, of the ground surface or objects on the ground that has the Newtonian gravitational field, but it's oscillating, it mimics the gravitational wave thing.
So Dreamer and I will discuss these long-term issues in a lecture.
Okay. So I guess quickly, so it just shows that you can play with the figure so that the low frequency can be improved, but you need larger mirror masses, but you need low laser power. And this might not be as interesting as using other, probably more advanced optical design, but nevertheless, this is possible. So as this configuration it is, you have to do this in order to improve low frequencies. While in the high frequencies, the shock noise is more important, and the only way, well, probably in this thing, is that you have to increase the laser power inside the arm cavity. And it turns out actually the thermal noise is not as important as in the low frequency band. So, of course, this curve shown is for low coding, for already reduced model of the projection of this estimates of thermal noise in future. And so you see here, so here I'm showing several curves to show the effect that when you increase the laser power, how are you going to increase the sensitivity at high frequencies? So the two curves here, the blue and green one, are showing 800 kilowatt circuiting power, which is comparable just to the LIGO 2 design. And by changing the optics, you can either gain more bandwidth, or you can have higher sensitivity, but in the price of lower bandwidth. But anyway, you cannot really, so there is a constraint. And in order to really increase broadband in the high frequency regime, you really have to increase the circuiting power. For example, when you double the circuiting power, you can have a curve that is much higher sensitivity at high frequencies. And this curve is with there's also some thermal noise estimation where you see it's not quite significant. And another thing you can do at high frequency is to take advantage of this optical resonance and to use narrowband configurations. For example, it's shown here several possible narrowband configurations. And this is with the thermal noise, and this is thermoelastic noise, and this is without thermoelastic noise. You see that it is quite this kind of optical resonance is quite versatile in the sense that you can move around and find your specific astrophysical sources and optimize the sensitivity at specifically those frequencies. And apart from this signal recycling counter, there are also more advanced optical configurations, designs. One example is the speed mirror design, which is, I just briefly say that. So it's so previously we have talked about this conventional interrupter, which is strictly a monitor of this displacement. And then we talked about using this optical light to change the dynamics of the mirror. So you're measuring an oscillator, but so you have resonant peaks. But one way of gaining another relatively narrow band, but one way of gaining a broadband nice configuration that beats the standard quantum limit would be directly, well, it's not, you're using some optical techniques to measure the momentum of the test masses, because the momentum is not constrained by the standard quantum limit. So, for example, there are some works here that describe that design, and it turns out this designs at low frequencies are not susceptible to the radiation pressure noise, so it can have a relatively broad band. But up till now, either the LIGO 2 design and the speed mirror design, they all need relatively very high, not relatively, but very high laser powers in order to achieve this sensitivity at this level. So there are also some radically different designs where people hope they can get lower laser circuiting powers. For example, there is the Berginski's group in Moscow is studying what is so-called an intracavity readout scheme. So they still use the light here, and the light is still relatively strong, but not so strong. But the laser light in the in the cavities are not really used for readout, because all these mirrors are all perfect mirrors. But they put some intracavity mirror so that the light force will make this guy move. And somehow the light is used as a transducer of the gravitational wave motion into the internal mirror motion. And other additional readout schemes here using smaller scale devices are employed. So that's a radically different thing. and finish.
So it's maybe worth emphasizing on this intercavity system, what you're doing is you're transferring the gravity wave signal to the motion of an object relative to local inertial frames.
Yeah.
In a normal interferometer, all of the mirrors remain at rest in their local inertial frames, and the relative motion of the mirrors is caused by the motion of the inertial frames relative to each other. That's what a gravity wave is. And so you can't go make a measurement, say, of the end mirror of an interferometer relative to a local inertial frame at the end mirror location and see anything.
Yeah. So this guy has to be here.
Yeah. So you have to somehow transfer all the motion of the end mirrors to onto something and force it to actually move relative to local inertial frames, and then you can have some big advantage in building a measuring system because you can do it all locally. Which is what Yanbei was saying. Any other questions? Okay, on Monday we're going to have a change of pace. We're going to go away from interferometers for a little while and have a discussion of gravitational wave detection by Doppler tracking of spacecraft. John Anderson will come down from JPL and do that. They actually are in the middle of observations, they've taken their data, they're in the middle of data analysis on a vastly improved experiment with this technique. And then I will talk about gravitational wave detection by pulsar timing. And then we will return for several lectures to discuss data analysis. Actually, Albert Lazzarini on Wednesday will discuss data analysis for LIGO. And then the following week, I forgot, I think the following week we may be moving on into bar detectors and other things. But there will be one more lecture by Drever and me on the ultimate limits on how well you can make LIGO. But that'll be later. But the lecture is bounced back and forth in topic because of people's schedules. I tried to keep them in a logical order, but to people's schedules, lecturer schedules have forced us to bounce back and forth. So next week will be the first departure from interferometers into other kinds of detection techniques.
Okay. We failed.